Okay, exponential growth is a way of explaining how a population is going to change over time. And this is different from, say, a linear growth model, where linear growth, the population grows by the same number each time. Well, with exponential growth, instead of that, you start with a given population. After one time period, that population grows. After the next time period, each of the members of the new population grow at the same rate that they grew the first time, so you end up with more. So what ends up happening is instead of going up, say, 6 each time, you may go up 6 the first time, 36 the next time, and 216 the next time, and so on. So in order to figure out what the population is going to be at any particular time, we need to use some different formulas. There's two ways we can do it. The first way is recursively. And what that means is we're going to use the previous value to calculate the new value. So the previous value being sub n minus 1, the new value being p sub n being the number of time periods. So the way that this is going to work, we start out with our problem here. The population of gremlins is 1. After it gets sprayed by water, the population increases to 6. If each subsequent population gets sprayed and increases by the same amount, how many will there be after 4 sprayings? Well, we can find out the populations, but before we really can do anything with that, we need to know what R is. And for this purpose, the R, the growth rate, is the new value minus the old value divided by the old value. So for what we have here, R is going to be the new value of 6, since there's 6 after the increase, minus 1, because that's the original value, divided by 1, which is 5. And since typically rate may be expressed in percentage, that is a 500% growth rate. That's a 500% growth rate at this point. So now what we're going to do is recursively, we're going to find out how many gremlins you can expect at this particular growth rate. So p sub 0 is before any growth occurs. That's going to be our given value in this case, which is 1, because we just had 1, population hadn't grown. P sub 1, then, is simply going to be 1 plus, our rate is 5, times p sub n minus 1, which is going to be p sub 0 in this case, right? Because n is 1, p sub 0 is going to be 1 from right here. So that gives us 6, which matches what we said it was going to be. After 2 growth periods, p sub 2, it's still going to be 1 plus 5, because the growth rate is still 500%, times p sub n minus 1. Well, if p sub n is 2, n minus 1 is going to be 2 minus 1, or 1. That's going to be 6, which is 36. P sub 3 is still going to be 1 plus 5. And now, since we're at p sub 3, p sub n minus 1 is p sub 2, which is 36. Which I'm not going to be able to do that one in my head, I don't believe. Comes out to be 216. And finally, p sub 4, after the 4th spraying, 1 plus 5 times 216. So 216 times 6 comes out to be 1,296. Now, as you can see, this could be problematic if you had to figure out, say, the 15th or 20th generation. It's going to just keep on going and going and going. So mathematicians have come up with a better formula that does it explicitly. And explicitly means you know which p sub n you're looking for. You just plug in the values and try it and see what you get. So p sub n, in this case, we're looking for the 4th spraying. So p sub 4 simply equals p sub 0, which we said was 1, times 1 plus our rate, which was 5, to the 4th spring, which becomes 1 times 6 to the 4th, which is just 6 to the 4th, which is 1296. So you can see you end up with the same value either way. So that is how exponential growth works. Back here, this is only going to occur with one growth period. Okay. Now, what if we don't know the growth rate and we need to find it out? Well, you have to be a little careful with this because most people, when they first try to do these problems, think linear. They think linear growth, so what they're going to do, and I'm going to write this down as linear, they're going to say, oh, well, we'll just take our 3,500 minus the 1,600, and that gives us, what, 1,900, and then we just divide that by 3, right? Well, that would only be true if the total population grew exactly the same each time, but it's not going to. So we need to find the growth rate. Okay, so the way that we're going to do this, I know the rate of change that we talked about before, that was actually a linear growth rate, and that only really applies if you just have one growth, one time period. In this particular problem, we have 3 time periods or 3 springs. So we can't do that. We cannot assume that it's going to spread the same amount each time. So to find the growth rate, what we're going to have to do is plug it into the growth rate formula. So that's p sub n equals p sub 0 times 1 plus r to the n. And notice what we're looking for is r. We don't have that. So if we use the values that we have, we end up with 3,500. That's p sub n. Equals p sub 0, which is 1,600, times 1 plus, we don't know what r is, and n, there was 3 springs, so that's 3 time periods. So we're just going to solve this equation. We'll divide by 1,600 because we're undoing the multiplication. And what do we get? 3,500 divided by 1,600 comes out 2.1875. Pardon me. Yes, 1,600 springs. Okay, 2.1875. Sorry, I was just checking my numbers there. I thought I had an error, but I believe I've got this correct. And then this is going to be equal to 1 plus r cubed. Now, we still need to get this r by itself. We can't subtract the 1 because we've got this thing in an addition problem raised to a power. So we have to do the opposite of raising it to the 3rd power, which is to take the cubed root. Now, on your calculator, you may have a button that looks like this. You're welcome to use that if you want to. Or you can also, a cubed root is the same thing as a 1/3 power, just like a square root is a 1/2 power. Either way, you're going to be able to do it. I'm going to use this button right here on my calculator. I wish I could show it to you, but with this tablet, I can't very well do that. But I'm going to take the cubed root of 2.1875. So that's going to be 3 cubed root button, 2.1875. Comes out to be 1.298. 8, 1, 2, and a bunch of other numbers. That equals 1 plus r. Now, anytime you end up with 1 plus r, this is known as the growth ratio. And you may see that in the homework, so I just want to make sure that you're aware of that. But we were looking for the growth rate, so we simply subtract 1. And that gives us r is equal to 0.29812, or roughly 29.812% is our growth rate. Okay, so you can see that because there was more than one time period for this growth to take place, you can't just use the linear formula that we showed you on the previous slide. So you can see in this particular example, the growth rate was 29.812%. Okay, and finally, if you know that your gremlin populations grow at a rate of 40% per spraying, that would be our R. About how many sprayings will it take to have around 5,000 gremlins if you start with 1? So again, we're still going to use the same formula. P sub n equals P sub 0 times 1 plus R to the n power. Well, P sub n is what we end up with, which is 5,000, equals P sub 0, which was 1. 1 plus, the rate is 40%, move the decimal 2 times, that gives you 0.4 to the n power. So let's go ahead and simplify what we can here. So we got 5,000. And 1 times anything is itself, so we don't have to worry about the 1. And inside parentheses, 1 plus 0.4, it comes out to be 1.4 to the n power. Now this is where one of the videos that is presented in the homework assignment comes in handy, is how are we going to get in any form that we can actually find it? Well, in order to do that, it can no longer be an exponent. So the way that we convert exponents into numbers is using logarithms. So what we're going to do is take the log of both sides. Log of 5,000 equals log 1.4 to the n. But again, as it always works out, a logarithm is an exponent. See the other video for more details on that. N is an exponent, so we have an exponent raised to a power. And whenever you have a power to a power, you multiply them. So this is the same thing as n log 1.4. This is still log 5,000. So if you have n log 1.4, this is n times log. So to get rid of the log of 1.4, we're going to divide by log. 1.4 divided by log 1.4. So you're left with n on this side because these cancel. And on your calculator, you just type in log 5,000, close your parentheses, divided by log 1.4, close parentheses, and you find out you're looking at 25.3 and a bunch of other stuff, but roughly 25.3 sprayings. Now, can you do a third of a spraying? 0.3 is roughly a third. Can you do a third of a spraying? Probably not unless you manage to spray 1/3 of the 5,000 gremlin, or 1/3 of the gremlins that you happen to have to get to the 5,000. So basically it's about 25 or 26 sprayings. Hopefully this helps you with your growth problems, and if you need any further assistance, just feel free to contact your instructor.